Okay, we're live. Yep, that works. Okay. So, lesson 3. Can everybody take a look at this? Not as much writing on this one. We're only going to basically do one definition and then we're going to play a game. So lesson 3, theoretical probability. Theoretical probability is a ratio that compares the number of possible successful outcomes to the number of possible outcomes, I should say number of total possible outcomes, and it's determined by reason or calculation. Experimental probability is a ratio that compares the number of times an event occurs to the total number of trials or tests, and it's determined by experiments. Okay, there is a little bit of a game we're going to play a little later. It'll be fun. But before we do that, we're going to write down the following here in this space on this page. We're going to write down, we're going to try to write down, come on, come on. Okay, would it help if we made this bigger? Yeah, made the whole thing bigger, there we go. And we're still not writing for some reason. And I don't know why the pen's not working now. There we go. We're going to write down what's called the law of large numbers. And here's what the law of large numbers says. If a probability experiment is done fairly and its possible outcomes are random, then the experimental probability will get closer to the experimental probability as the number of trials gets large. There we go. Now that's a sentence. Check that out. It's kind of too long, but oh well. We'll explain what we mean by that once you catch up to my writing. People at home can't see this if you're watching this video, but take my word for it. In my right hand, I have a fair six-sided die. It's a great big blue one. And I'm going to now just roll this die. I'm going to roll it 6 times. A 3, a 2, another 3, a 4, another 2, and a 1. I will now conclude from that, you don't have to write this down, just think about it, that the probability of rolling a 2 on this die by my experiment is 2 out of 6, which is 1/3. Is that a good valid conclusion? No, because I only rolled the die 6 times. What is the actual theoretical? So this is now, again, this is an experimental probability because I did an experiment. What's the actual theoretical probability? 1 out of 6, right? So the probability of a 2 is, right, desired over possible. How many 2s are on this die? Right there, just that one. How many possible? Oh, wait a minute. I just wrote the number 2 and I meant to write the number 1. There's only 1. 1 out of 6. So there's a big difference. 1 out of 3 is actually twice as big as 1 out of 6. So what's the problem here? What's wrong with my conclusion from my experimental probability? Yeah, the number of trials I did is way too small. I could maybe add to this. I hope that you wrote a little smaller than me. Making a conclusion, generalization, or inference about a probability based on data. I'm going to have to write over here. From a sample size that is too small is an invalid conclusion. So, is my conclusion that the probability of getting a 2 on this die is 1 out of 3 a valid one? No, because I didn't do enough experiments. The sample size of my experiment was too small. What should I have done? Maybe I should have rolled it 60 times. Maybe I should have rolled it 100 times. Well, it doesn't matter as long as I understand that the bigger the number of times I roll it, the more likely this fraction would have gotten to be closer to 1 out of 6, assuming it's a fair die. Yep. How about I shrink it so that you can see more of it? Does that help? There we go. Can you see that from back there, though? That makes it smaller. You get it? Okay, sorry. I'll slow down a bit. My apologies. I know a lot of writing here. That's about it for writing. I'm actually going to talk a little bit now about something that we don't really talk about much in this course. They expect that you did this in grade 9. That's why it doesn't really pop up in the course. And we actually won't test you on it, but it's a really important idea in probability that I do want to talk about. If you're out of room on this page, you might want to just jot it down on loose leaf. Kevin, you should put your phone away and pay attention. Okay. Now I've already told you I'm anti lottery ticket because lotteries are, as the great mathematician Pascal once said, the lottery is a tax on people who are bad at math. So they want you playing in that hope that you'll win the big prize. The statistical likelihood, the probability of you winning it is so small. You'd be far better off, far better off taking the, what is it, $2 for a ticket, and say that you played it I think the big lotteries are now twice a week, right? So that's $4 a week. Take $4 a week for 20 years, save it and invest it. You'll have a far better return on your investment than throwing it out the window at lottery tickets. But every once in a while, say that there's an office pool or something. It's like, okay, pick numbers because we're going in the office pool. I'll just say, fine, leave me alone. I'll pick 1, 2, 3, 4, 5, 6. And people go, well, no, do this seriously. And I said, that is serious. I'm going to pick the numbers 1, 2, 3, 4, 5, 6. They said, well, there's no chance that that'll be the numbers drawn. I said, there's just as much a chance that those numbers will be drawn as any other numbers. And they said, but we've never seen a draw like that. Well, of course you haven't, because there's 14 million draws, and in your entire lifetime, you're only going to see a very small fraction of that. So you're not likely to see any specific 6 numbers, and my 6 numbers are just as likely as your 6 numbers. So I'm going to pick 1, 2, 3, 4, 5, 6. Now, of course, a lottery is not one event. I know you buy one ticket, you're trying to win. You could kind of think of it as one event, but it's actually 6 events. And again, if you need to use loose leaf because you're out of space, use loose leaf. In probability, this is the part that you were supposed to learn in grade 8 or 9. A lot of teachers don't get to this stuff in grade 8 or 9, so this might be news to you. The curriculum assumes you know this and doesn't cover it, so let's just talk about it real quick. The odds, or the probability that 2 different things will happen combined into one number is called independent events. So for example, what is the probability that you will roll, oops, I just misspelled roll, that you will roll 6 on a die and flip heads on a coin? So what's the probability that they'll both happen? It's 1 out of 12. Because what do you do with the 2 numbers? Somebody remembers it from junior high. What do you do with the 2 numbers? What are the 2 numbers? Well, the probability of rolling a 6 on a die is 1 out of 6. Probability of flipping heads on a coin is 1 out of 2. What do you do with those 2 numbers? You multiply them. You multiply them when they are independent events. Here's the rule in kind of mathese here. If event A does not affect the likelihood of event B, probability of A and B is equal to the probability of event A times the probability of event B. The key word here being and. And means multiply in probability. So yeah, what's 1 out of 6 times 1 out of 2? Now, there might be people going, oh great, fractions, that was what I hated in junior high. I was bad at it, I never remembered. Do I need a common denominator? Actually, no you don't. But feel free to use your calculator if you want to. You got a fraction button? Run it through. This is an easy one to do without a calculator. Top times top, bottom times bottom. It is 1 out of 12. If you have your calculator and you have a fraction button, you can use it to help you with that. Dependent events, this is a little more complicated. This they don't really talk about much in grade 9. Grade 9 is all about independent events. The opposite of independent events is, of course, dependent events. And for dependent events, the probability of A or B is equal to the probability of A plus the probability of B. So say, for example, I want to know the probability of either rolling a 6 or flipping a heads. Well, okay, how does that work now? Well, let's see. What are all the things that can happen? What we're going to do now is we're going to draw ourselves a tree. It's going to be a strange looking tree. But I'm going to draw, let's see, what's the smaller part of this tree? Well, the smaller part of this tree is flipping the heads and flipping the coin. When I flip a coin, I can get either heads or tails. So let's see. If I flip a heads and then I roll the coin, I can get a heads, then a 1, or a heads, then a 2, or a heads, then a 3, or a heads, then a 4, or a heads, then a 5, or a heads, then a 6. After I flip the tails, I could roll the die and get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. That is, in total, 12 outcomes. Right? What is the probability that either I get a 6 or a heads? Well, that's this answer here. I get the heads and the 6. That's either. It's both, really, but that counts as either. And then there is all of the, then there's the tails and the 6. And then I could get a heads and a 1, a heads and a 2, a heads and a 3, a heads and a 4, a heads and a 5. So add all that up, and what do you get? There is 1, 2, 3, 4, 5, 6, 7 out of 12. So it's an add. You have to add up all of the possibilities. There's 12 outcomes, right? Desired over possible. Let me go back to this here. Go back, come on. Right? Desired over possible. I haven't heard one in a while. Okay, so I'm sure they're fine. All right, let's do another tree diagram. More tree diagrams. One more. Let's do a tree diagram for use a tree diagram to find the probability of flipping a coin three times and landing heads all 3 times. Okay, so let's make a tree diagram for that. So what does my tree diagram look like? It looks something like this. Here, I'll give you a sec to catch up to me. And where did my coin? I had a coin. Oh, I must have put it away. Yeah, you sure? We're going to be done here in a minute if you don't mind. Just wait. Yeah. This will be the last example, then I'll let you have some more time. Okay, so what does the tree diagram look like? Here's how we make a tree diagram. The first roll of our coin, the first flip of our coin, we could get either heads or tails. After I flip heads, I could flip the coin again and get heads, or after I get heads, I could flip the coin and get tails. See where I'm going with this? After I flip tails for the first time, I could get heads the second time, or tails the second time. After my second flip, I need to do a third flip. So after the second flip was heads, I could get heads again or tails. After the second flip was tails, I could get heads or tails. Heads or tails. Heads or tails. So, how many possible, so remember probability is desired, I keep writing this formula down, over possible. So how many things do I want to have happen in this chart? How many of them are a success? Just this one, right? Heads, heads, heads. One desired thing. How many possible outcomes were there? 1, 2, 3, 4, 5, 6, 7, 8. 1 out of 8 is my answer. That's all we expect you to be able to do in this course, is do a tree diagram and count. The more sophisticated way is to go back and go, were these events dependent or independent? Ask the coin. Say, coin, what did you land last time I flipped you? Does the coin know? It does not. The coin is random. The coin doesn't know, doesn't care. The coin is a 1/2 chance of heads or tails every time. So that's the very definition of independent events. Event A doesn't have any effect on event B. So event A is my first flip. Event B is my second flip. In this case, event C is my third flip. So without the diagram, I just misspelled diagram. Diagram. Without the diagram, the math is probability of heads, heads, heads is 1/2 times 1/2 times 1/2. And what's that going to be? Again, if you're not good at fractions, you can use your calculator. Come on. Top times top times top. What's 1 times 1 times 1? Still 1. What's 2 times 2 times 2? We get the same number. And now that we know how to do that, we can answer something very sophisticated. So this will be our last example. What is the probability, and I just misspelled probability, probability. What is the probability of a ticket winning the Lotto 649? Now, I don't know how the Lotto Max works, because I don't honestly know how many different numbers you have to choose from, but I know this one very well. So first of all, why do they call it the 649? Because you have to pick 6 numbers, and there's 49 numbers to choose from. Get it? 6 out of 49. If they put all 49 balls in a big drum, like a big sphere, kind of like a bingo game drum, if you've ever seen one of those, right? And air pushes them around, and they bounce all over until one of them goes into the little slot, into the little hole, and they pull that ball out and say, there it is. This number just got drawn. Then they don't put it back, and they draw the next one, and the next one. Now, does the first ball have any effect on whether or not the second ball is going to be drawn? No. So they're independent events. So 6 things are happening. And for you to win the big prize, you have to get all 6 of them. Now, this math gets a little hairy to do without a calculator, but let's give it a try. 6 things are about to happen. The chance that the first ball out of the drum is one of the balls I picked, well, think, it's desired over possible, right? So what do I desire? I desire one of 6 numbers that I've picked. How many numbers are there possible? 49. So the chance that I will get 1 ball right is 6 out of 49. Then they draw another ball. What's the chance that that's one of my numbers that I've chosen? Well, they can't draw the same ball again, and I can't pick the same number twice. So the chance that the second ball that comes out of the drum is mine is 5 out of 48. What's the chance that the third ball that comes out of the drum is one of mine? You can probably see a pattern here. What's the chance that the fourth number they draw is one of the numbers I've picked? And what's the chance that the 5th number is one of my numbers? And what's the chance that the last ball they drew is one of my numbers? Okay. Now, you could run that through your calculator, but I have a shortcut for you. Do you remember back when you were learning how to multiply fractions? Don't worry, I'll move that back in a sec. Do you remember when you were in grade 8 learning how to multiply fractions? And I'm sure some people here went, oh, I know how to do that. Top times top, bottom times bottom. Oh, and then I've got a fraction I have to simplify. And there's people who go, okay, How many 6s go into itself once, and then 6 goes into 24 4 times? At some point, your teacher probably said, you know, would you like to avoid having to do this step? There is a nice way to do that. Anybody remember it? Yeah, cancel. The reason I was able to simplify 6 out of 24 is because 6 goes into 6 and 24. But I can see that right here. 2 goes into itself once and into 8 4 times. 3 goes into itself once and into itself once. Instead of 2 times 3, it's 1 times 1, which is 1. And instead of 3 times 8, it's 1 times 4, which is 4. So back in grade 8, they tried to teach you that, oh, when you're multiplying fractions, why don't you look to simplify it before you multiply it? Ooh, that kind of rhymes. Simplify it before you multiply it. And that's what I'm going to do here. I really don't. 6 times 5 times 4 times 3 times 2 times 1 is 120. That's not too hard. But I haven't the slightest clue what 49 times 48 times 47 times 46 times 45 times 44 is. And I don't care to find out. It's probably too big to even show on the screen of my calculator. So I'm looking for cancels. Do you see any? How about 5 goes into itself once and into 45 9 times? Your turn. See any more cancels? Oh, come on. There's lots. 4 goes into itself once and into 48 12 times. That's a good one. See any more? You know what I'd like? Is I'd like to make the numerator all the way down to 1. 1 times 1 times 1 times 1 times 1. So keep going. See any more? See any more numbers on the top that have common factors on the bottom? Sure you do. Come on. How about 6 goes into 12? Yes, you can double cancel. 2 times. Oh, how about here's a 2 and a 2? Oh, if only I could get rid of that 3. Are any of the numbers on the bottom divisible by 3? The 9 is. So instead of the top being 6 times 5 times 4 times 3 times 2 times 1, I got 1 times 1 times 1 times 1 times 1, which is 1. Now the denominator is still going to be an awfully big number, but not nearly as big as it was before I canceled. 49 times 47 times 46 times 3 times 44. Punch that in the calculator. I actually already know what this number is going to be. It's almost 14 million. 49 times 47 times 46 times 3 times 44. 13,983,816. The chance that the ticket you bought is the winning ticket is 1 out of 13,983,816. Go back to our homework. Some of you have started this assignment already. The rest of you will start it today, and you can work on it today. But people were asking me about this question yesterday. They were saying, what do we do with this number 1 question? Well, you kind of just guess where on the scale the answer goes. The first one's kind of hard. Let's go to one that's easy. What is the probability that the next baby born in the Victoria Hospital will be a girl? Anybody know? What is the probability that a baby is going to be a boy or a girl? 1/2. It's the same. 1/2 boy. So where's 1/2 on this number line? There. So that's D. This is the one people were asking about A. I don't know how. I don't know. Guess. Do men in your family, guys, tend to live a long time? Oddly enough, women, it's not as easy to think to predict for you. But for men, if there's a history of heart disease in your family, you're going to get it too. So do men tend to live long in your family? If the answer is yes, then maybe you've got a shot. But still, do half of the population make it to 100? No. I don't know. For me, I'm going to say it's pretty much here. I don't think there's much chance. I'm a big fat guy. I don't exercise much. I don't smoke. That helps. But I think certainly my dad made it to 80-something. My grandfather made it to 70-something. I'll be lucky if I make it to either of those things. I'm going to pick my A chances as here. That's just a guess, obviously. Okay? Okay, let's think about, if we put an F down there, chances of winning the 649, what do you think? That would be so close to 0. Could you even see 1/13 millionth of this line, or 1/14 millionth of this line? No, it'd be 0. On the other side of the scale, the sun will rise. Oh, sorry, the sun will rise in the east tomorrow. Wait a minute. Where does the sun rise? Doesn't the sun? It rises in the east, and it sets in the west. Is there any chance that it'll rise in the west? So that's a certainty. That one goes there. All probabilities are between 0 and 1. That's basically what that question wants you to understand. You will get 80% or higher on this unit? Well, that depends on you. What do you think? What are your chances? Are you on the left of the scale or the right of the scale? You take your pick on that one. Okay, I think that's all I really need to kind of tell you about. You can work now. Okay, yeah, there you go. Yeah. Do you not have this book yet? I'll get you the book. So, okay, let me go back, and I'm going to stop my video. That's all I needed to talk about today.